Hello, and welcome to today's webinar presented by Delubal Software. Today, we're working in our structural analysis and design software, Rfem 6. The topic for today's presentation is ACI 318 2019 Isolated Footing Design in Rfem 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions that you may have today. They are both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So regarding the content over the next hour today, I do want to give a brief introduction into the Concrete Foundations add-on within Rfem 6 that we have enabled the ACI design checks. We will then move on to our example within Rfem directly, where we will define our isolated footing geometry. We will input in the reinforcement. We will also define the soil layers. After this, we'll go ahead and set up the load cases and load combinations according to the ASCE 7. I'll also show you how you can apply additional foundation loads directly to the isolated footing. And then we'll run our calculation for both the analysis, but mainly focusing on the foundation design results. And finally, at the end of the presentation today, I do want to quickly integrate our additional add-on called the steel joints with the foundation to do a quick base plate design and show the advantages there. So turning now to this brief introduction, I will go ahead and explain the advantages here of the concrete foundation add-on that you can find within Rfem 6. So this now allows us to carry out the isolated footing design within the global Rfem 6 model. We can essentially define the geometry of the footing. We can input in top and bottom reinforcement, and we will also input in the soil definitions. So this is required for the soil underneath the footing, but also around and on top of the footing is possible. After we run the calculation, we will see the design checks for this footing for one-way shear, two-way shear, and flexural design according to the ACI. But we're further going to carry out these soil-related design checks, more relevant from the IBC, including overturning, sliding uplift, and bearing pressure. A big advantage here is that we are getting the full integration with the global 3D structure included loading. So you can see our example structure over here on the right-hand side. Any of the loads that are applied directly to this steel structure will be considered for the foundation design. But it is also possible to consider additional foundation loads. Again, we'll see that in the example today. Now, the true advantage here is that we are able to design this entire structure, including members or surfaces. We could carry out the connection design of both the members, including the base plate, and the foundations in one file. So we're not having to export out the support reactions to a standalone program or a third-party program, but everything is integrated together directly within Rfem. So with that said, we will get into the program directly today to begin our example. So when we create a new model within Rfem 6, we are presented here with our base data dialog box. The type of model will be in a 3D environment. Under the second tab are the available add-ons within Rfem. So you can essentially create a software package that is specific for your design needs. And for those of you joining us today that are not familiar with this add-on concept, the Rfem 6 base program is always required. This allows us to integrate with BIM software such as Revit, Tekla, AutoCAD, Grasshopper, Rhino, or we can directly model within Rfem itself, where we have access to all of the cross sections and the materials from the various standards implemented. So we can apply loads and get a full static analysis. But the minute that we want to carry out the design according to the various standards, we would need to activate the relevant design add-ons. So you'll notice for today, I do have the steel design add-on activated. This is not going to be a main focus for today, but it is just to show that we can carry out the design of the steel members within this model. But the primary focus will be the concrete foundations add-on, which is activated here. Under the third tab are going to be where we set our standards. So we can generate the load combinations automatically according to the ASCE 7, the latest 2022 standard. We also can generate snow and wind loads according to the ASCE 7, which we'll briefly touch on that today. Now, because we have activated the foundation add-on, the concrete design and geotechnical analysis options are activated here, referencing the ACI 318. The steel design is also activated, as I mentioned, to carry out the steel member design checks according to the AISA 360 2022 standard. So once this information is set, we have determined here which standards we will be referencing. We can take a look at the Rfem 6 program. So for the sake of time, I have already modeled our steel structure here. So we'll do a quick model overview to explain exactly what I've already went ahead and modeled in the graphical view. We have our cross sections defined. So you can see the columns are 14 by 82 with our beams set at 18 by 35. These are tapered members. So I did extend the depth where it does frame into the column here slightly. Both of these cross sections are A992 materials. I also have square HSS members. So 6 by 6 by 0.375 defined here for my purlins and my secondary members. This is A500 grade C material. And finally, we just have some round solid steel sections here for our lateral bracing. These are 3/4 inch diameter A36 material. You'll also see here the colors are based on the member type. So shown here in blue for our moment frames, this member type is a standard beam. And in RFEM, a beam is anything that's a standard beam or a standard column, nothing too unique about it. Alternatively, we have our members shown here in green, and these are going to be truss elements. The advantage of a truss element is that we automatically apply a moment release at the member end, so you can see why the hinges is grayed out. Now, this is in contrast to the beam member, which by default is considered fully rigid at its member ends unless I manually want to apply in some type of moment release or pinned member end connection. And finally, we also have our tension only members. So exactly as the title denotes, these members can only take tension forces. The minute that they see compression forces, they are taken out of the calculation. But because RFEM is a nonlinear analysis program, if tension is reintroduced in a subsequent iteration, then we will reactivate these members. So that will summarize here a general overview of the structure that's already modeled. We now want to move on to our foundation definitions. And there's a couple ways to go ahead and define these initial isolated footings. Well, you'll notice here within the graphical model that I have my nodal supports defined at the base of each of these columns. Well, under the types for nodes, we'll find this nodal support definition. I can go ahead and double click on it to bring up this dialog box. So I have a standard pin nodal support, and it is applied to all of the nodes at the base of the structure. From here, we can activate the ability to assign a foundation to this nodal support definition. So in the second tab that's now available here, I can begin defining my isolated foundation. So it's important to know here that the axes orientation for my foundation are based on the local axes of these nodal supports themselves. So if I wanted to rotate my foundation, I would actually need to rotate the nodal support itself, which I can do so by selecting this first option here. And then we have the available options to rotate the axes. We'll actually get into this topic a little bit later on with our example. With this will be required. But it's also important to know that the same foundation geometry reinforcement input will again be applied to every single uh, column here at the base of our structure. If we wanted to modify the geometry, so let's say the two interior columns have differing geometry or reinforcement versus the outer columns, then we would want to define here a new nodal support definition and assign that to the relevant columns. So again, I just want to emphasize here that the foundations are assigned directly to the nodal supports themselves. Now, alternatively, rather than going through this dialog box, what we can do here is to go ahead and cancel out, and we have our concrete foundations folder available to us. So this is enabled because I have activated this add-on where I can right click to create a new isolated foundation. And this allows me to further select the nodal support definition graphically so that I can continue defining this footing. So again, a couple different options here. If I had additional nodal support definitions, I could create additional isolated footing definitions using this option in the lower left-hand corner and assigning it to the relevant nodal support number. We will start off though with our isolated footing essentially the same at the base of all of our columns. So let's get into the definition here within the dialog box. The type of footing is set to pad foundation. So this is just a standard isolated footing. The second option here is unreinforced. So if we were not interested in applying reinforcement, carrying out the shear and flexural design checks from the ACI, but we're still interested in carrying out those geotechnical design checks like sliding, overturning, bearing pressure, we could choose the unreinforced. For today, we certainly want to carry out both. Now, the rest of the foundations are not applicable yet for ACI, so we'll just go ahead and focus on this one for today. The material would be defined for our foundation, which we could access our material library. And over on the left, we have the ability to use our filters to set the region to the United States. The material type is set to concrete. We have the ACI standard set, and we can select 4,000 PSI concrete. Now, if you have a compressive strength and a material that's not listed directly in the library, I would suggest to just go ahead and bring one of these library options in. When we go ahead and click OK, we have the ability to always edit this material, and we can modify this to user defined here in order to modify the compressive strength, for example, as well as the other material properties. We can rename it. We can add that to our own library for future Rfem models. But for today, 4,000 PSI concrete is relevant. The design properties is activated here by default. This is just telling the program that not only do we want to set up our footing, but we also want to carry out the design according to the ACI and the IBC checks within the foundation design add-on. The second tab is to define the geometry of the footing. So we will go ahead and input this in based on the local X and Y axes of the footing itself. And for today's example, this will be 84 inches by 84 inches. Now, by all means, this does not necessarily have to be a square. It can be a rectangle. Those dimensions can vary. The thickness of today's foundation will be 18 inches. The eccentricity, so this is by default set to 0, which just means that this column will frame in directly at the center point of this foundation. If we do have an eccentricity or that offset, we can go ahead and define those dimensions here within this input. The column dimensions are automatically brought in. The program recognizes the dimensions of this W shape here, so those are not editable. But what we can do is to further specify a base plate at the base of our column. And this is going to be used for the load distribution at the top face of the footing for the design, but also this will come into play at the very end of our example today, where we can integrate this with the base plate design. So the dimensions here will be 18 inches by 18 inches, and the thickness is going to be 1 inch. So now that the geometry is set, we can move on to our next tab for the reinforcement. We do need to define here a reinforcement material. So once again, we access our material library. Over on the left, we can choose the reinforcing steel as the material type, the ACI standard, and we do see here grade 60. So I'll go ahead and use grade 60 for today, but again, user-defined materials are entirely possible. The reinforcement type can be set to a welded wire mesh, it can be set to rebars, or it could be set to both. For today's example, we will use rebar reinforcement. Now notice there is an automatically checkbox here. It's grayed out. This is for a future release where maybe we want to automatically determine what the reinforcement is. But for right now, it does require manual input of the reinforcement. The concrete cover tab allows me to input in a different concrete cover at the top of the footing versus the bottom versus the side. Now, if all covers are identical, I can alternatively turn this off and set my cover for today's example to 2 inches. The plate reinforcement. So this is where I'm going to specify in here my reinforcement at both the top and the bottom of the footing. So you'll notice by default, the top reinforcement is set to none. So in many cases, we may not need top reinforcement, but in other cases, if we do have high flexural loads at the top there, then perhaps we want to toggle this to define our reinforcement in both the longitudinal and transverse directions. For today, I am not going to apply any top reinforcement, so we'll go ahead and set this to none. But the bottom reinforcement, we certainly want to define that here. So I can zoom into this picture and just show you that the primary direction here can be toggled to X or to Y direction. So notice that that will go ahead and move that reinforcement bar to the top layer here. If we change this back to the X direction, which is what we'll move forward with today. Again, these are just based on the local axes of the footing itself. So I can select my bar size directly within the dropdown. For this case, we will choose number 6s spaced at 12 inches on center. In the transverse direction and the Y direction, this could vary, but we will also set this to number 6s at 12 inches. Now you'll also notice we can define here a hook anchorage length, which does include the length itself as well as the bend diameter. This will be taken into consideration with development length checks. That's not something that we'll take advantage of today, so we can go ahead and turn that off. Now that the reinforcement has been defined here, we do have a nice feature that I can access to show the reinforcement layout in the bottom right corner. So when I click this option, this does give me a nice plan view of the reinforcement in both the transverse and longitudinal directions. It shows me the length, it shows me the number of bars, the size. I can turn this into an isometric view if I'm interested. We can go back to elevation views or a plan view. If we had additional reinforcement defined at the top versus the bottom, we could go ahead and deactivate those various layers here. And once this is set up, we can use the print options here to add this directly to our printout report or our calculation report. You could send it to a PDF or a 3D PDF, or you could save it to your clipboard. So many different options here, but again, just an overall nice layout of the foundation reinforcement. So moving on now to the soil properties. The soil properties are absolutely needed here in order to carry out those geotechnical design checks, like sliding, overturning, bearing pressure, and so on. The first input option here is the subsoil conditions, drained versus undrained. This is going to affect our sliding design check, so you would want to specify the condition there. We'll go ahead and set this to drained. Now, down at the bottom of this dialog box, you'll notice that we do need to define here the soil layer under the foundation. So this is always required. And for this, we can once again access our material library. We can use the filter settings over on the left to choose the material type soil. I do not have any standards selected, so this is code independent. We do have some default options available directly here within the material library, including gravel, closely graded. And that's what we'll use, for example, today. Now, most likely the soil materials available here are not going to be exact for your project. So what I would suggest that you do is to choose a material that maybe most closely fits to your specific design project. We bring it into this dialog box, and once again, we can always choose the edit material options. Now for soil, we always have this set to user defined so that you have the ability to override the name here, but more importantly, the material values. So for example, specific weight, the density, jumping to the material values, there is some important information here like effective friction angle that's used for sliding, for example. So you would want to get this information from your geotech report and input it into the soil properties directly. Again, those are going to be used for the design checks. So again, for today, we'll go ahead and use the material option, gravel closely graded under the footing itself. In addition to this, we have the ability to specify here the soil layer next to the foundation. So I can use the same material or I could select a different material. And now you'll notice that this picture over on the right-hand side updates to include the soil around the foundation edges. Now, it is important that once we get into the geotechnical configuration settings, that we enable the passive pressure to be considered from the soil. Without enabling this, the soil in and around the foundation will not be considered. And this will make more sense once we get to it, but we can activate that element here for now. The third option is the soil layer on top of the foundation. So once again, I'll choose my same material here. And when I activate this, I get a new option here to define the earth covering thickness. So if I set this to something like 1 foot, you'll notice that I have an additional layer now given to me on top of the footing itself. And we'll also see how that's applied as an additional foundation load once we get into our loading details. Just quickly looking at the other soil parameters here, we do have our angle of soil friction. This is related to sliding checks, and this is going to reference directly the material's effective friction angle. So I pointed that out in the material input. Again, maybe it's something that you get directly from your geotech report. The angle of wall friction is going to be a consideration of the foundation sides and the surrounding soil, again, related to sliding, also related to the soil layer next to the foundation slab. We can define a groundwater level. So when we activate this, we can specify the depth here. Now, if we had something very extreme at the top of our footing, you can see that update here. This essentially will have buoyancy effects in our design checks. So if you don't have any groundwater, that it's not really a concern, you can always deactivate that here, which is what we'll move forward with today. We then have our geotechnical configuration settings. So the design configuration for geotechnical is again going to be those soil specific design checks. And we go into the default option that's set here. And it should be noted that you can create multiple design configurations for different foundation input. Now, for today, I only have one foundation, so therefore I can only have one design configuration. But if we had different foundations with different sizes and we wanted to modify the configurations, those certainly could be created with this button in the lower left-hand corner and assigned to the relevant foundation number. Now, the first input setting here is the consideration of the factor loads for the foundation design. By default, these are all turned off, but if you want to deactivate one of the loads, so we have here the loads in the translation directions, X and Y. We also have our vertical load in the Z direction, and then moments, MX and MY. So therefore, if you wanted to neglect one of these for the foundation design, you could do so. We then have these safety factors for sliding and overturning. And we do reference here the IBC 2021 section 1807.2.3. This section is actually more specific to retaining walls, but it could be the industry standard to still apply the same safety factor of 1.5 to isolated footings as well. But if that does not fit your design needs, you have the ability to override this. We also have the ability to check the soil bearing pressure. With that requires the user to input in the gross allowable soil bearing capacity. So gross meaning it does include the footing and soil self-weight. This is surely something that you will get from the geotech report. For our example, we'll go ahead and set this to 3 kips per square foot. Then we have the sliding check. So again, this is activated, turned on, where we want to input in the coefficient of friction. And for the coefficient of friction, we could reference the IBC 1806.2, which includes some presumptive values, but the value should really also be based once again on the geotech report. So for our example today, we will use the suggestion from the IBC of 0.35. And here is that passive earth pressure option that I had mentioned. So remember, we had placed soil in and around the footing itself. The default option here, which is more conservative, is to actually ignore that soil for our sliding checks. But if you want to consider it, you can go ahead and activate this checkbox here to consider the passive earth pressure. And then there are further 2 options. The passive earth pressure can be considered according to Coulomb's theory, or you can directly define these resisting forces yourself in kips in the global X and Y directions, both positive and negative. So both options are available there. Again, the more conservative option is to leave this unchecked. So we'll go ahead and use that for today's example, ignoring that soil at the foundation sides. Then we further have overturning, uplift, and we also do a design check of the loads with large eccentricities. Again, these are all activated by default, but if you did want to turn these off, that's certainly possible. So once we have defined this information, we have the final tab here for the concrete configuration. And this is going to be related to the reinforced concrete settings for shear and flexure. So we'll go into the default settings here. The first option is related to the ACI section 9331. So if we wanted to ensure the element is tension controlled, we could go ahead and activate this checkbox here. The next input settings are just the strength reduction factors according to section 2121. Pretty self-explanatory. For compression, tension, shear, we refer directly to the code for these safety factors. We then have the minimum reinforcement according to the standard. So there's a couple different checks that we have. The first being the minimum longitudinal reinforcement according to section 7611 and 8611. Well, this is more specific to one-way and two-way slab elements and the minimum reinforcement required there. The alternative is according to section 9612, equation A and B, which is more specific to beam elements. So depending on on your footing type, you would select the relevant option here. There is an additional check for the minimum longitudinal reinforcement due to two-way shear. This refers to ACI section 8612. And finally, we have the epoxy factor. So essentially, is the reinforcement uncoated or is it epoxy coated? This all comes into development length design checks. Go ahead and leave this as uncoated for today. So now that this information has been set for those reinforced design checks, we are done with the input here within our isolated footing. So we can click OK, and now we see the graphics update back in the Rfem model. So our relevant footing is now placed at the base of each of these columns. You'll notice the reinforcement is also shown graphically here. The nodal supports are still shown. If you're not interested in viewing those graphically, we could always visit our navigator here. And all the way up at the top, we could turn off the types for nodes if we wanted to see the column frame directly into the foundation. Again, we're just hiding that graphically, but they still do exist. We now want to move on to the loading. So we're going to activate here our load cases and combinations dialog box. Now, under the base tab, if you remember, we are generating the load combinations automatically according to the ASCE 7, the 2022 standard. When this combination wizard checkbox is turned on, those will automatically be created. Alternatively, if I want to uncheck this and to manually create my load combinations, I could, but today we certainly want to utilize this. Under the load cases tab, there are 4 simple load cases for today. And a lot of these will be relevant to the structure itself rather than the foundation. But we do have here dead load, live, wind 1, and wind 2. And the one that is going to be very relevant, though, to our foundation design is the dead load. So notice that the action category is set here within the drop down to dead load based on the ASCE 7. By default, self-weight is automatically included here for the entire structure within this load case. But you will see here an additional checkbox, the self-weights for concrete foundations. Now, just to quickly show this, when I uncheck this option, I lose this additional tab here. When I go ahead and turn it back on, you'll notice that it's reactivated. So taking a look at this, the first option here is to consider the self-weight of the foundations itself. So these foundation elements are not FEA elements. They're not surfaces, they are not mesh. You can think of it more as an analytical design approach, but therefore the self-weight is not automatically considered for these foundations. So therefore, if we do want to consider it, we do so within this additional checkbox option here. And this will also, of course, affect some additional design checks within the concrete foundations add-on itself. The earth covering. So if you remember, we placed a 1-foot depth of soil above our foundation. So it's not until I come in here and I activate this earth covering, am I going to see the additional loads applied to the footing. And I'll be able to actually graphically see this within the Rfem model. So we'll take a look at that in just a minute. Also, groundwater, we talked a little bit about that for buoyancy effects. If we want to consider that, we also need to activate that option here. Now, we don't have any groundwater effects for today, so we can go ahead and turn that off. Now, looking at the design situations, the program will automatically create 2 design situations for me. And you can think of a design situation as grouping together the load combinations from the ASCE 7. So we have here our first design situation for our factored load combinations. And then we have a second design situation for our unfactored load combinations. Again, we're just going to be referencing the ASCE 7 here to generate those load combinations and placing them in this design situation. This is going to come into play a little bit later on with the limit state types within the concrete foundations design. But if we're most interested in seeing the load combinations listed out individually, we visit this last tab. Here are my factor load combinations in orange belonging to that first design situation. And here are my unfactored load combinations in red belonging to the second design situation. So now that we have our load cases and combinations set up, we would want to ensure that the loads are now applied to the structure. So I toggle here to my dead load where I'm going to turn on the display of the loads. Now, again, for the sake of time, I have already applied the loads to the overall steel structure. So just quickly going over these, I did take advantage here of our load wizard, the member loads from area loads, where I can define these planes here to find the magnitude, and then the program will automatically distribute these based on the tributary area directly to my moment frames. So that's just a simple dead load here. I also have a small pre-stress force applied to these tension only members. So it could be that under gravity loads, these are immediately deactivated because they're in compression. We have instabilities because we have no further lateral restraint. So therefore, for this one, I did apply an axial displacement for a small pre-stress load directly to these members under the dead load case. Okay, so that's as far as the structure, but let's focus in here on the foundation itself. So you'll notice that I do have a surface load essentially applied to the entire foundation here. So this is going to be for that soil that was placed on top of the footing that I defined within the concrete foundations dialog box. This is that 1 foot depth. We know the density of the soil, we know the area, so therefore we can apply this load to the foundation itself. Now, the question might be though, well, what if we want to apply additional loads to the foundation? And I had mentioned that this is not a two-dimensional surface element. I don't have the ability here, like I do other RFEM elements, to apply a nodal or a line load. Instead, we have a special setting here for additional foundation loads within this dropdown. So this is available because the foundation design add-on is enabled. So when I choose to add this additional foundation load, what you can see here is that I have 3 different load types. I can apply a surface load, I can apply a line load, or a concentrated load. Now, for my example today, let us assume that we have some additional slab element that's going to be constructed and framing into these isolated footings, but it didn't actually model it in RFEM directly. So therefore, I want to place a line load at the inside face of this footing to account for maybe some of that additional loading from the slab. So I'm going to apply an additional foundation load as a line load, and I can graphically select the foundation to apply to. Now remember, because we have one foundation definition, it's going to apply the same load to all of the foundations. I click OK, and I can specify here the load magnitude, which is going to be 0.2 kips per feet. I can then toggle my view here to ensure that I place this line load exactly where it's needed based on the local X and Y axes of the foundation element. So I can apply the coordinates, which will be set as X1 of 36 inches. Y1 is going to be set to negative 51 inches. X2 will be 36 once again, and Y2 will be positive 51. So we see that line load update accordingly here in this graphical view. And when I click OK, I am brought back into the global RFEM 6 model where, once again, I know it's a little bit difficult for you guys to see, but there is this line load that exists in addition to this soil load. Now, the problem is that the line load looks great on the left side of our structure, but when I look over at the right-hand side of the structure, that line load is on the outside face of my footing, which is incorrect. And the problem here is that all of these foundations share, again, the same nodal support definition type, which means that the local axes of the foundation are oriented in the same directions as the nodal support themselves. And maybe just one thing to quickly mention, if you're interested in seeing the local axes of the foundation, we can always go into our navigator. All the way at the top here under concrete foundations, we can display the local axes. And I'll go ahead and turn this into a wireframe view. And I'll zoom in here so that you guys can see these local axes available. So this will be helpful in defining loads, knowing orientations, but I'll go ahead and deactivate that. So how do we deal with this load then being at the incorrect location? Well, this is where we'll go back to the beginning of our example where we have these nodal supports defined here at the base. And I likely want to create a new set of nodal supports at the right-hand side of the structure here so that I can orient the local axes of the foundation facing inward instead of outward. So what I'll do is I'll go back to the navigator, and under types for nodes, we have already visited this dialog box for the nodal supports. Remember, we have this single definition applied to all of these nodes. I'm going to make a copy of this. So again, just a standard pin nodal support, but I'm going to graphically select here all of my nodes using my selection box at the base of the structure. So the nodes are populated here. I click OK. And what you'll see now is that I have a new nodal support definition of the left versus the right of the structure. And for this new nodal support, I am going to rotate the axes. So I activate the specific direction option here, and I'm going to choose to align the local x axes of this nodal support based on two nodes. So I'll go ahead and select the base of the structure as node 1 and then node 2 as the left-hand side. Now the z-axis is still oriented in the vertical direction, nothing different there. So when I click OK, you'll notice now that this line load is oriented at the inside face. So again, just trying to emphasize that the nodal supports greatly affect our foundation input because those two go hand in hand. Um, Alternatively, just to take a look at the concrete foundations, you can see here that this single definition type is now assigned to nodal support number 1 and nodal support number 6. If I wanted to assign different geometry or different reinforcement, I could certainly delete number 6 here, create a new definition type, make my changes, and apply that to nodal support number 6. Okay, but for today's example, they are going to have the same geometry and reinforcement input, so no changes are needed there. So that's going to sum up our dead loads. Let's just quickly take a look at our live load. Again, this just really affects the structure itself. Taking advantage of that load wizard option, I just have a live load applied directly to the moment frames here. And for my two win loads, I did also take advantage under the load wizard of the win load generator according to the ASCE 7. So this is possible for general rectangular type structures here. I only have a couple simple load cases here for minimum win loads according to the ASCE 7 in the global X direction, which we can display those loads separately. See how they look here. As well as wind in the global Y direction. So we'll right click to go ahead and have an area load view. We can toggle down to our different load combinations here to see the dead load, live load, and wind loads all acting on the structure together. So now that the loads have been applied directly to our foundations as well as the steel structure, I am going to drop down here to the concrete foundations add-on. And within the table, you will see the two design situations listed. So we have our first design situation for factor load combinations where I want to set the relevant limit state type within this dropdown. So we're going to set this to our strength design checks. I then have my ASD design situation, so unfactored load combinations, where I'm going to set the geotechnical design limit state. So this is how those design situations come into play within the design add-on, such as concrete foundations. Under the second tab, Objects to Design, we will be designing all foundations because we only have one definition for our foundations today. Under the Objects to Exclude, we do have the ability here, if we did not want to consider one of the load combinations, to uncheck that within the table option. So now that we have input in the relevant limit state type for the design situation, let us take a look at the results. So we can go ahead and run this calculation. The program will cycle through all the load combinations, taking advantage of the multi-core processor in our computer. So we should see this solve rather quickly. And then we carry out the foundation design, and we are now presented with our results. So we'll start first with the navigator view over on the left-hand side. So we could toggle back to the static analysis within the base program Rfem 6, but our focus today is the concrete foundations design results. And graphically, we have the ability here to activate our design checks for both the soil as well as our ACI design checks. Now, if I just want to see the max controlling design ratio, I can go ahead and activate that here, and I'll go ahead and zoom in on a couple of the foundations. Alternatively, if I'm interested in viewing the design ratio for these individual design checks, so for example, under the geotechnical design, I can activate the allowable soil bearing pressure design check. Or if I'm interested in uplift or overturning, this is possible to view individually. Alternatively, if we want to turn now to the concrete design checks, we could activate here the design checks for bending, for the bottom reinforcement in both directions. We also have the one-way shear design check as well as the two-way shear design check. So this is available again to toggle through these individual design checks here, show them graphically. In addition, we also have the reinforcement that we can display graphically. So what this means is that we have applied these loads to this footing. And from those applied loads, there is some required reinforcement, which we can actually display that graphically here. So you can see the required reinforcement in both the transverse and longitudinal directions. Well, if you remember, we placed number 6s at 12 inches on center. So this is my provided reinforcement, which I can certainly display that graphically as well. Well, what we can do further is to compare the provided reinforcement to the required reinforcement. And we can have the program tell us, okay, is any additional reinforcement required? In our case today, you'll see here 0 is displayed because my provided reinforcement is greater than the required reinforcement. So just a nice graphical view here of those reinforcement requirements that we can display graphically on the footing itself. Okay, so going back now to, let's say, the table design checks. We can go ahead and display here if we want to keep this graphical view of the design ratio. But within the table itself, we can view the design ratios based on the design situation. So this is going to be my factored load combinations for those strength design checks, and then unfactored for the soil design checks. We can view the design ratios by the foundation, which just means this is going to be an overall envelope solution for our design checks, or we can view the design ratios for each node. So notice as I scroll through this table, this red arrow is showing me exactly which footing I'm currently looking at. But going back to the design ratios by foundation, we also have the ability, not only in this table format, to see these design ratios, but we can activate here the design check details. So if I take a look at sliding, for example, and I activate the design check details, this is going to show me in much more detail with all of my formulas, the variables, any code references here, and ultimately how we determine this design ratio for sliding in particular. Now, over on the left, we have additional information that we can expand here. We can add this to our printout report as an image. If we make any modifications, these formulas will automatically update in that printout report. So trying to be very transparent so that you understand where these design checks come from. Now, in a similar sense, we do the exact same thing for the ACI, reinforced concrete design checks. If we take a look at two-way shear, we can activate, once again, the design check details. This is going to have quite a bit more formulas specific to the IBC, or sorry, the ACI rather than the IBC. We can scroll down through and ultimately the final design check here for two-way shear. So we are essentially passing all of the design checks for our foundation here. If you are finding that you're failing, this will require some modifications to the foundation. So we can just go ahead and double click on the foundation itself. If, for example, we were failing in sliding, perhaps we want to make some changes to our geometry. If we were failing any of those ACI design checks, we maybe want to make some modifications to the plate reinforcement here. So yes, we could certainly make those modifications, somewhat of an iterative process to ensure that we are passing those design checks. So that will summarize here the overall foundation design using the Concrete Foundations add-on. But I now want to quickly tie in the ability to perhaps design something such as a base plate. So how these two can kind of work together. For this, I am going to go ahead and revisit my base data dialog box by just right clicking on the model name here. And under the add-ons, we have the ability to activate here the steel joints. So the steel joints is certainly a very powerful and unique feature in the sense that we can design the steel connections of members to members, but we also can do base plate design. And with this, we always build up an FEA model underneath the hood for any connection. This is really powerful in the sense that we are not limited to standard connection design, but really any connection is possible. So now that we have activated this additional add-on, I visit my second standards tab here where the AISC 360 will be used for our design, as well as the ACI. So for our base plate, we are doing additional ACI checks for the anchor bolts, for example. So now that this is activated, we can click OK, and we have a new folder for steel joints. So I can go ahead and double click on this to create my steel joints definition. And this one does allow me to individually select nodes. So it's not based on the nodal support definitions. It's based directly on the nodes themselves. So you can see here all of those nodes are imported in. I am not going to consider those tension only members for this quick base plate design. We're only going to consider the vertical members. Well, under the components, I have the ability here to insert in a new component, very simple for today's example, for a base plate. So I can bring that in and we can see the graphics update here. And of course, we will need to make some modifications. Now, alternatively, if I have a more complex connection or I just want to quickly utilize the library, which has these components already set, I could use my filters over on the left to filter to a total of one member. And we can select here a base plate. You can see some different options here, again, for maybe more complex base plate situations. Down at the bottom, though, there are some simple template options that you could import in to your model. But for our case today, the single component input is certainly applicable. Now we have the ability to import in the geometry from the concrete foundation. So this is how these two can more or less work together. So when I activate this, notice that my geometry definitions were automatically updated here for the foundation concrete block and also for my base plate. For the plate material, we will modify this to a 36, but again, all the dimensions were brought in from the foundations add-on. My concrete block, same thing, 4,000 PSI concrete, the material and the dimensions were brought in. There are some additional settings here for crack concrete, reinforcement to control splitting, grout, so on, that we could turn on or off. Now, the shear transfer, this can be set either to anchor bolts or to a shear lug. For example, today we'll go ahead and use anchor bolts. This will be a 36 material and the diameter will be 3/4 inch. Now, we clearly need to make some modifications here to where our anchor bolts are placed, and we are going to have a total of 4 anchor bolts in the longitudinal direction and 2 rows in the transverse direction. Now, we still have some conflict here, so therefore we want to modify the spacing. So the spacing from the edge of the base plate to my first anchor bolt is going to be set at 3 inches. And then the additional spacing will be 3 times 4 inches. And the program will go ahead and update this graphically. The spacing from the front edge of the plate to the center of my first row is going to be modified here to 2 inches. And then the spacing to my second row will be 14 inches. So when I make those modifications, we can see here that we no longer have that conflict with our column. And of course, you can play around with the number of bolts here. Perhaps we only need 3 or 2. We can play around with different diameters. The length is going to be set at 12 inches to extend down into our footing. We also can modify here the anchor type. So we'll set this to a hex head, for example, and everything is displayed graphically. The final input is going to be the welds of our steel column to our base plate. We'll go ahead and set this throat thickness to 0.27 inches. I hit the F8 key to go ahead and apply that same dimension to all of my welds. So that's really it for the quick input. If we want to double check the plausibility, we could, to ensure that there's no errors found. Everything looks good here. Now, before we jump back into the Rfem model, there's one more really powerful feature that we can take advantage of here. And that's to calculate the true base plate connection stiffness based on all of these elements. So I can activate this option within the steel joints add-on. And for my columns, I can tell the program that I want to determine the true stiffness of both the axial and rotational stiffness itself of the base plate, because we know that these connections are not truly pinned, they're not truly fixed, they're usually somewhere in between. So because we're generating this FEA model automatically underneath the hood, we can determine this true stiffness. And furthermore, once we determine this stiffness, we can export it back out to the global model for my columns. So now at the base of my column, I'm going to have a member hinge applied that's going to be considered for both the analysis and the design. So now that this information is input within the model, we can take a look at graphically here by displaying the detailed joint model. And I can zoom in here. Let me go ahead and turn off my nodal supports under types for nodes, and I will go into a solid rendered view. So we can see the footing, we can see the base plate, and of course the steel structure. Now we do want to run the calculation for the steel joints as well. For this, I'm just going to toggle to an already finished model because this does take just a minute to solve. But under the steel joints design, we are carrying out the design of the welds as well as the anchor bolts. And this is all referencing directly the codes such as the AISC and the ACI. So this is an envelope solution for all base plates here. If I want to take a look at the design check details, just like what we saw with the concrete foundations, all of these formulas are going to be listed out, including information like the concrete breakout tension resistance, the pullout resistance, the blowout. These are all listed here in order to determine the controlling design ratio here for these anchor bolts. Now, as far as the plate elements, again, we are generating this FEA model underneath the hood and comparing all plate elements to a limiting strain value. And if we're interested to pull up the submodel that's created underneath the hood, we can go ahead and activate that within the model. Now, underneath, we are going to, once again, I'll go ahead and toggle this here to equivalent stresses. The submodel does include, of course, all of these elements like the base plate, flanges, web, but it also includes a spring stiffness underneath the base plate to represent that concrete foundation. But we can view the stresses here on the base plate. We can view the tension forces on the anchor bolts as well as stresses within the weld element itself. So just kind of shows you how those two will work together. But if you also remember, I had calculated the stiffness analysis here. So we see the true stiffness of this base plate connection for axial and rotational stiffness. And I had mentioned that we can automatically export this out to the member end. So if I take a look at this one-dimensional column here, I have the hinges activated and I go into these detail settings. The program has automatically created these various diagrams for rotational and axial stiffness directly from the steel joints add-on. So you can get very detailed again at the member hinge, at the base of this connection, everything working together for both the analysis of this member, but also the steel design. So just kind of a unique feature there. Maybe just to quickly mention, if you remember way back when, I also carried out the steel design of all of these members. So you can see here, we're not going to get into it, of course, we're out of time today, but all of the design checks for our members are carried out according to the AISC. So for example, we're currently viewing the lateral torsional buckling mode shape here of our beam. So we can actually see how this would fail according to LTB. And very similar to the other design add-ons, we can always activate the design check details to see all of the code references and formulas and ultimately how we're calculating the member design ratios. So full design of the structure, including the members down to the base plate, down to the foundation within one file. So with that said, we'll go ahead and wrap up our webinar today. I do want to just briefly touch on future developments for the concrete foundations add-on. We are currently working on stepped footing design, so that will be next to be released. We're certainly aware as well that the 2025 ACI standard has been released, so we're currently working on getting all code updates updated there as well. We want in the future to consider the input and the design of dowels within these foundations. I already talked about too, just better optimization for both the geometry and the reinforcement, maybe requiring less manual iterations if we are not passing those design checks. So certainly some improvements to come there. We do want to also extend this to include the Canadian code, the CSAA 23.3, as well as other foundation types. So in the future, you can expect these other foundation types like combined footing, strip footing, and so on. But for now, this is a good summary of what is possible with the isolated footing design. So if you were interested in what you saw with the Foundations add-on, Rfem 6, or any other capabilities, and you want to connect with our team, we would love it if you would go ahead and scan this QR code, or the information, the contact information to our Philadelphia office is shown at the bottom of the page here, our phone number and our email address. Would love to get you set up with the 90-day trial version. So this is full capability. It includes all add-ons for the full 90 days. We will have many more upcoming webinars. You can register at delubal.com under support and training webinars. As most of you know, I tend to send out a reminder email before these take place. So keep an eye out in your email for the next webinar to come. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you're here for the full 60-minute duration in order to receive that PDH. If you watched with a colleague or you watch in a conference type setting and you yourself did not register for the GoToWebinar, you will need to request that PDH at the email address shown here, info-us@dulubal.com. You'll just want to ensure you were here for the full duration, let us know who you watched it with, and request that PDH by sending us a quick email. And with that said, I want to thank everyone for attending. There will be a very short survey that pops up when you exit this GoToWebinar. It's a tremendous help to us if you just provide your feedback about the webinar, your feedback about RFEM 6 and what you saw today, again, to help us just improve both our webinars and our software in the future. And with that said, thank you again, and we hope to see you at the next presentation.